This is the PowerPoint for this is entirely out of the paper that's in your proceedings. I didn't want to put the paper up there and make you read a whole page full of text, so that's what I put this together for. And in honor of all of the people from marketing who bother the fire out of us with wild PowerPoint presentations, I have attempted to make the animations of this one as annoying as possible. So don't blame me. It's all those people that we're usually mad at when they do crazy things with it. But that's the easy one.
Those must be really good routines.
And one of the only missing features in the WP34S to many of us were matrix routines, or things that could handle matrices to do determinants, inverses, things like that. I mean, it's an incredibly complete function set with many things I still don't know what they are. But many of us kind of thought, oh, we need some matrix work in here. When we asked the developers, they suggested do it yourself. You know how it is, right? You want something, you volunteer to do it, so go right ahead. So Jake and I decided to do it. And that smiley face is also something that shows up in marketing people. But the question is, where to start? All right, I am not a math major. I had a minor in math. It was a long time ago. Never even took linear algebra. So what am I doing writing matrix routines? Well, the good news is I don't have to start from scratch. There's a great deal of material out there that is easily adaptable to work on the 34S. And that happens to be the PPC ROM, of course. Thank you. Roger, Jay. You know, all right, so we've paid our homage. Because when I had to do some determinants in graduate school or whatever, I was using the PPC ROM anyway, so why not try to port those over to the 34S? How difficult is it? The short answer is it's easy. So, the PPC ROM had matrix routines, of course, M1 through M5 that did various utility sorts of work for matrices that could form the foundation of larger programs. And those called other supporting routines, which were QR. All right, we all know what that is, or who knows? Call it out.
Quotient remainder.
You have to be quiet, Richard. Anybody that was not Richard, Jake, or Roger.
Or didn't hear him just now.
Or didn't hear him just now. Somebody in the back, call out. What is QR?
Quotient remainder.
Quotient remainder is what that one is. It's a routine in the PPC ROM. What about BX?
Branch and exchange.
No. We're not talking assembly language. The B is a block. So that's block extreme. It returns the largest, or I think perhaps the flag setting, the smallest number in a block of registers. And BE, the true, real, only bug in the PPC ROM, that even Richard acknowledged in a later journal, block exchange. The PPC ROM, that's a bug because it's the only place I believe, Richard, here's your thumb drive. It's the only place I believe where a go-to should have gone to a local label in a loop, but it got coded and put into the ROM as a go-to to a global label, which meant it invoked, the only place that happened, the entire search chain through all of the global labels in the PPC ROM, and there you had how many? 120, right? And so that was the only crying point of the PPC ROM that Richard gave out loud. That's the only thing I know of really that really went wrong. And it's real easy to spot how that can happen with everything going on with a utility routine. So you got to have those in there too. The PPC ROM manual also had two other application programs to help, RRM and MIO. MIO is for matrix input and output, to give you some formatted prompts to know what register you were loading or what matrix element you were loading. And RRM is row-reduced matrix, right? Row-reduced echelon, whatever form, for a matrix is the solution. So these were, of course, were standard HP41 programs that were actually very easy to convert over to the 34S. If you have the printout in front of you, or a manual or a PDF of a 41 program, you can almost always directly convert them over. They're fairly easy to do. Here, you're going to like this one. Yeah, look at that. So we adopted the matrix routines. Yeah, there you go. The whole slide's going to do it this way. I thought it was actually going to do the whole page as I talked, but I've got to keep hitting this. All right, so here we go. In order to run these routines, you had to store the starting matrix element number, what register it was going to hold the first matrix element, into memory 7. So if you're going to start, you could relocate that. So if you wanted to start in register 10, you put a 10 in memory 7. You want the matrix to start in register 30, you put a 30 in register 7. It's the pointer for where the matrix elements start. You store the number of columns into register 8, you store the number of rows into register 9, and you store the matrix in row order, okay, beginning when the register entered in step 1 above. So if you have a 2 by 2, 1, 1, right, that element would go into whatever register 7 is pointing at. You start with 10, which is the first available. The matrix element 1, 1 is put into register 10. 1, 2, 1 over goes into 11. 2, 1 goes into 12, and 2, 2 goes into 13. Without MIO, you've got to do all those stores manually and remember where you are and what number it goes into. That is a pain. It's an incredible pain. Because you just keyed one in and like, what number did I put that in? Was it 47 or 48? I don't remember. So Jake helped out a great deal by porting over to the 34S, the MIO routine. And as somebody said yesterday, I think Neil, you were pointing out, those alpha commands are really kind of troubling because it's kind of one letter at a time unless you use Neil's assembler these days, which can do it a whole lot easier for us. But Jake put that together. If you're going to compute an inverse matrix, you have to actually store the identity matrix of zeros and ones in the larger matrix element. So if you have a 2 by 2 and trying to do an inverse, no, it's not a 2 by 2 anymore, it's a 2 by 4. Because you have to have 1, 1, 1, 2, and then 1, 0, and then the second row of the matrix, and then 0, 1, I think. You have to store those zeros and ones by yourself into the registers. If you're doing a system of equations, you have to put in the matrix, the identity matrix, and then the column of constants, the coefficients, all keyed in manually, one at a time. Hey, what we're trying to do is we're trying to at least do a matrix routine, and the MIO does help a great deal with viewing the matrix elements as well as keying them in. The memories used by the program itself are 0 through 9, so that's why you can start putting things into memory 10. So it's very destructive. This doesn't live well with other things that are in your 34S because it assumes, hey, 0 through 9 are mine. I'm going to do with them what I want. It uses flag 10. You have 90 available registers. It's actually 91, I guess, isn't it? No, it's 90. I always have to subtract out of there. You have 90 elements, so you can do a 9 by 9 determinant. That takes 81 registers of the 90. You can't do a 10 by 10. It's not enough directly accessible memory registers without some special tricks in the 34S. You can do a 7 by 7 inverse because you have to have not only the elements but the identity matrix stored in there, and I think that takes 2 to the n squared registers. So 49 times 2 is what? 98? Is that right? Didn't fit? I'm trying to think. It's probably a 6 by 6. I think I messed it up. Let me think about it a second. 7 by 7, 49. Yeah, it's a 6 by 6. It should be. And you can do a 6 by 6 system because that's n times 2 to the n plus 1, or 2 times n plus 1. That's all in the paper. I know I've done a 7 by 7 because I made it work. The programs that we did, you know, I'm not a real expert on all the extra 34S commands like SDR, shift right, shift left, and all these extra wild things that are in there. There's a lot of ways to really enhance this program. But the key is, even I got a matrix routine running that would do a determinant without knowing any of that stuff. And so if you know how to program the 41, or you have a listing from someone who knew how to program the 41, if you can find the commands, you can probably key them in and get the thing to work. So most of the 34S software base can come directly from existing 41C programs. You have a PDF of the PPC ROM routines as well as examples of the RRM program, and you can download them here. That's a tiny URL pointing to a Dropbox link. That's just an 8 or 10 page PDF.
That's in the
From the, it's in, this link is in the proceedings. It's from the PPC ROM manual, so if you have one of those, you have that as well in there. And so then I decided, all right, well, how does it do? So I did a determinant of matrix AM1, and I posted this on the museum a couple of weeks ago. AM1 is Valentin's special matrix where the determinant, the true determinant, comes out to be 1. Okay, and it looks deceptively simple. Because this is your matrix over here. You know, there's not any real crazy elements to that. They're all 2-digit integers. Well, when you compute it, you get these answers for your determinant on these models. And as you can see, the 34S is quite good at that. It gets the best result I have ever seen, unless you're using the 50G or 49G plus and allowing it to cheat. Because there's a flag setting, I think it's the tiny element flag and maybe one other one, and it pre-scans somehow or other the matrix. Somebody objected to my statement of that on the museum. It can't pre-scan anything. Well, all right, but if you set the flag, what it does is it looks over here at these and says, oh, by the way, these are all integers, the determinant should be an integer. And so it makes the determinant an integer. I consider that cheating, because it's not really doing the mathematical computations behind it and potentially losing accuracy for it. Yes, Mark?
Yeah, on the 50G, if the numbers contain a decimal point, then it'll store it as a real. Otherwise, it'll be the infinite precision integers. And so in that case, it would do the exact precision determinant.
Well, I do know that there are a couple of flags, too, that can adjust even things that are approximate numbers. But the key is, look, my keying in, essentially, of the 41C PPC ROM routines and the RRM application program give a better result than the 12C does, 15C does on that matrix. The 15C gets essentially 1.08 for the determinant. Your 34S, faster, can solve the determinant of that matrix and get 5 9s and a 7, which I consider good enough, being a finance person.
Faster than the 15 CLE?
It is faster than 15 CLE. It did this determinant. I thought I put the program in wrong, because the 34S did that 7x7 determinant in about 2 seconds. How on earth is that possible? But 2 seconds, it was able to do it. The 15 CLE takes 7 or 8 seconds. I mean, you know, that's still pretty quick, but I really thought I had done it wrong. You know, you get an answer, it's like, that's too fast. It can't possibly be right.
I wonder how long the old 41
I had somewhere the timings for it, and the old 41 took several minutes. The 41CL still took longer, much longer than the 34S. And in many, many cases, it's going to be very tough to beat the 34S unless you're dealing with, what does Polly say, logarithms. He doesn't like logs because the calculation for that's pretty slow, and a few other things. But even though I had that, you know, once you throw something out there, there's something for people to chew on. There's something for people to say, all right, fine, I don't like this, it's too inelegant, it takes too much space, so we'll actually create a few things. And Jake and I are very happy to be that roadkill. I'm putting this stuff out there for somebody else to come and generate a lot of good stuff. Well, apparently, either very shortly or very, very soon, there are going to be a lot of matrix commands that will be added to the 34S. And, oh, I thought I'd fix this, so I didn't. There you go. We get multiple stuff coming in. How about that? All of these commands, and I think these are going to be these are the names as of right now. The names are still subject to change, stuff like that. But there will be a matrix transpose command, a matrix multiply command, some commands that are similar to what the PPC ROM did. So yay, you know, Jake and I writing this stuff out means the PPC ROM will live on by having some commands that do essentially the same functions as those PPC ROM routines, perhaps in our 34Ss. And then all of these over here. The approach will change a little bit. It's in the paper, in the proceedings, because he's going to use a block control word, more or less, or a matrix descriptor that has RR, CC, and then something on the end of it. But it's in the paper. I don't care. I just wanted the ability for us, if we have a 4x4, to just say, hey, what's the determinant of this? Or I have a system of equations, and I've got my 34S in the pocket, I'm on a desert island, I want to be able to solve it, so I won't be lost anymore. And these will certainly do that. So bravo to the 34S team, and I'm very thankful that Jake was helpful to get this thing running, and at least now, if you really want, you can do some determinants during lunch on your 34S. Tim?
You go back to your matrix.
The 7x7?
Yeah, just leave it up while you're asking.
Well, it's got all these things I got to go back through to get it through.
See it up there.
That is in the proceedings. I don't I mean, you can try it in Excel, but I don't think HP has a calculator out there that avoiding cheating will get a better result than the 34S. Yes, sir.
What algorithm do you use?
It's a row-reduced echelon. It does it in a row-reduced echelon form. I don't know. It's in the write-up that's at that PDF link. Again, remember, I had a math minor in college. I know what a determinant is, you know, all that kind of stuff. I'm all right with that, but I never had linear algebra, so I get to pass on that question. Thomas?
Have you looked into or considered instead of just complex numbers?
The question is about complex numbers. I think it was Pauly, actually, the 34S developer, suggested, well, why not use a complex recall for some of the stuff that doesn't look? Yeah, I'd take a pass on that. I'm hoping that it could be used for matrices of complex numbers like the 15C could, you know, stuff like that. But no, that I can do magnitudes of complex numbers. You know, I understand all that stuff for that. But you know, it rapidly gets beyond me, so I just say, hey, throw it out there, run over us a few times, and then hopefully somebody will do something a lot better and more fun.
Maybe comment on
Yes, Marcus, by all means, please.
Okay. You triggered the matrix routines Pauly is writing right now, so thanks for that. There are a few things to consider. First, if the 34S is slow at some times, it has to do with accuracy. So we are a team of three. Pauly is responsible for accuracy and some such. You want to give me this?
Yes.
Let's start over. Let's start over. It's not very well prepared presentation. Okay, we're a team of three, and Pauly is the guy who is responsible for accuracy and numerical algorithms. Walter is responsible for consistency, user interface, and I'm responsible for the fun of it.
That's important.
So what Gene did triggered Pauly to write some matrix routines, and the interesting thing here is that there are some things which should be done in user code and others which should be done in internal code. Accuracy being the main reason for internal code, and sometimes stack management, which is easier if you have a C routine instead of something which rolls a 4-level stack up and down without losing any information then. Accuracy, we have an internal accuracy BCD library written by Mike Colishaw of IBM, which is of arbitrary precision, and we use it to a precision of, I think, 39 digits, BCD digits. So this makes the log so slow. And if you do matrix operations, you often suffer from cancellation. And if you do this in internal math, with internal math, we get better results. So all things which might suffer from cancellation, so the fused multiply add operations should be done internally. Other stuff may be much more compact if done in user code. And we can do user code inside our firmware. We have a region of user code. So such as swapping rows and some such where accuracy isn't of a concern. This can easily be done in user code and is more compact. And we're always fighting the available flash size. So it's 128. We want to have user flash regions for you to store your programs. It's a programmer's machine in the end. And so it's a constant shift back and forth between those two ways to implement things, and that's the reason why this isn't done yet. Pauly is busily working on it. All those names have changed. Walter was involved, of course. So just replaced the lowercase t by a dot, which makes it more readable. We have some utility routines which help you to pass through elements of a matrix. So you just give it a matrix descriptor, which is a pointer to a register and information about the size of the matrix, and it returns you something which you can use on a DSE or ISG statement to go over columns, rows, and some such. Stay tuned. I think it will be maybe a week or two, and they will be ready.
Does that mean you're going to have a matrix button? Or
We don't have a
menu?
matrix button. It will, those commands will appear in some of the catalogs, so most probably the product catalog or the special functions. Some things which are implemented purely at user code without having a command name assigned to it. It will appear in the label catalog, so you can just pick a label. We have three letter labels on the machine. It's not as good as 41. But it's only the 34, it's not a 41. That's it from my side.
There is an HP machine that does better.
What? You're just going to make the